Imagine you could break every law of physics we know. Imagine you could travel at 1 light year per second, a speed so impossible, so mind-bendingly fast that it would take you just 4 seconds to reach the nearest star. What would you see? What wonders would flash before your eyes as you raced across the cosmos at speeds that make light itself look frozen? Today, we're going on that impossible journey together, and I promise you, what we'll discover will change the way you see the universe forever. And one quick question, if you could travel 1 light year per second, where in the universe would you go first? Let me know in the comments. I'll pin the most creative answer. Now let's begin. First, let's understand what we're really talking about here. Light travels at roughly 186,000 miles per second. That's fast enough to circle Earth 7 times in a single heartbeat. But even at that incredible speed, it takes light 4.2 years to reach Proxima Centauri, our nearest stellar neighbor. Now we're imagining traveling at 1 light year per second. That's about 31,500,000 times faster than light itself. It's a speed that would let you cross our entire galaxy in just 100,000 seconds, less than 28 hours. Starting from Earth, the first thing you'd notice at 1 light year per second is how quickly familiar space disappears. In less than a millisecond, you've passed the Moon. In 8 minutes worth of light travel time compressed into a fraction of a second, you've left the Sun behind. The entire solar system, from Mercury to the distant Kuiper Belt, flashes by in a blur, lasting less than the blink of an eye. But here's where it gets interesting. As you accelerate to this impossible speed, the universe itself would transform before your eyes. Stars wouldn't look like gentle points of light anymore. Due to the Doppler effect pushed to an extreme, stars ahead of you would shift so far into the blue end of the spectrum, they'd become invisible to human eyes, their light transformed into deadly gamma rays. Meanwhile, stars behind you would redshift into oblivion, their light stretched into radio waves your eyes could never detect. The cosmos would become a tunnel of light, with all the stars compressed into a brilliant ring around your direction of travel. This isn't science fiction, it's what physicists call relativistic aberration, just taken to an impossible extreme. 4 seconds into your journey, you'd reach Proxima Centauri. This red dwarf star, invisible to the naked eye from Earth, would flash by in an instant. You might catch a glimpse of Proxima b, an Earth-sized planet orbiting in the star's habitable zone. Scientists discovered this world in 2016 using the radial velocity method, watching how the planet's gravity makes its star wobble ever so slightly. But you wouldn't have time to stop and look. At 1 light year per second, you're already racing toward the Alpha Centauri system, a binary star system that would appear as a brilliant double star if you could somehow slow down enough to see it properly. Hey, if you're enjoying this cosmic journey so far, don't forget to hit that subscribe button and give this video a thumbs up. It really helps the channel grow and lets me know you want more mind-bending trips through the universe. Plus, you'll be joining a community of space enthusiasts who love pushing the boundaries of imagination. As you continue your impossible journey, you'd start to see the true structure of our stellar neighborhood. Within the first minute of travel, you'd pass dozens of star systems. There's Barnard's star, racing through space at unusual speeds. There's Wolf 359, one of the nearest stars to Earth and home to at least 2 planets. There's Lalande 21185, a red dwarf with a potentially habitable super-Earth. Each of these systems has its own story, its own collection of planets, asteroids, and comets. Some might harbor life, others might be sterile, but beautiful in their own way. At your impossible speed, entire solar systems become mere points of interest flashing by in the darkness. After about 10 minutes at 1 light year per second, you'd start to see something remarkable: the local bubble. This is a cavity in the interstellar medium carved out by ancient supernovae. Our Sun sits inside this bubble, which stretches about 1,000 light-years across. The bubble's edges are marked by denser clouds of gas and dust, the remnants of stellar explosions that occurred millions of years ago. The local bubble isn't just empty space, it's filled with extremely hot, thin gas. So hot, it emits X-rays that our space telescopes can detect. This discovery came from missions like ROSAT in the 1990s, and more recently from eROSITA, which is mapping the entire X-ray sky. As you race through the local bubble, you'd see the walls of denser gas approaching. These molecular clouds are stellar nurseries, places where new stars are being born right now. The Orion Molecular Cloud Complex would be one of your first major landmarks, a vast region of star formation that includes the famous Orion Nebula. But even the Orion Nebula, 1,300 light-years from Earth, would flash by in just 1.3 seconds. You'd catch a glimpse of the Trapezium cluster, young hot stars illuminating the surrounding gas, creating one of the most photographed objects in the night sky. The Hubble Space Telescope has revealed protoplanetary disks in this region, solar systems in the making, captured in their first moments of formation. As you continue outward, the disk of the Milky Way would begin to reveal its true structure. Our galaxy isn't just a random collection of stars. It's a vast spiral with elegant arms wrapping around a central bulge. From Earth, we see this edge-on, which is why the Milky Way appears as a band across our night sky. But at your impossible speed, you'd rise above the galactic plane and see the spiral structure laid out before you. The Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, each would be visible as dense rivers of stars, gas, and dust, connected by bridges of material and separated by darker, emptier regions. This view of our galaxy's structure isn't just imagination, it's based on decades of careful observation and mapping. Radio telescopes have traced the distribution of hydrogen gas. Infrared telescopes like Spitzer and WISE have peered through cosmic dust to map star-forming regions. The Gaia spacecraft has measured the precise positions and motions of over 1 billion stars, creating the most detailed three-dimensional map of our galaxy ever made. 20 seconds into your journey at 1 light-year per second, you'd be 20 light-years from Earth, passing through regions where some of the most intriguing exoplanets have been discovered. There's Gliese 667cc, a super-Earth sitting in its star's habitable zone. Scientists found this world using the radial velocity method, and it's been a target of intense study ever since its discovery in 2011. But something strange would be happening to your perception of the universe. At this impossible speed, time itself would become meaningless in ways Einstein never had to calculate. You'd be experiencing the ultimate cosmic slideshow, where entire stellar life cycles would seem to flash by in moments, stars being born, living for billions of years, and dying in spectacular supernovae, all compressed into your warped reference frame. Speaking of impossible speeds and their consequences, this reminds me why actual light-speed travel might not be the dream we think it is. In fact, I made a whole video about why light-speed travel would destroy us before we even arrive. The physics is absolutely terrifying when you really dig into it. But since we're already breaking physics in this thought experiment, let's keep going and see what other wonders await us. 30 seconds in and you're 30 light-years out. You'd start encountering some of the most studied stars in human history. There's Arcturus, the bright orange giant that's been guiding navigators for millennia. There's Vega, which was our North Star 12,000 years ago, and will be again in another 12,000 years. Each of these stars has been observed by countless astronomers, from ancient Babylonians to modern astrophysicists using space telescopes. The diversity of stellar types would become apparent as you race through space. Red dwarfs, making up 75% of all stars, would be everywhere, dim, cool, and incredibly long-lived. Some of these stars will still be shining 1 trillion years from now, long after our sun has died. Then there are the giants and supergiants, stars that have swelled up as they near the end of their lives, fusing heavier elements in their cores. You'd pass through regions where the Kepler Space Telescope found thousands of exoplanets. Kepler stared at one patch of sky for years, watching for the tiny dips in brightness that occur when planets pass in front of their stars. The data from this mission revolutionized our understanding of planetary systems, showing us that planets are the rule, not the exception. 1 minute into your journey, 60 light-years traveled, and you'd start to see the true three-dimensional structure of our stellar neighborhood. Stars that appear close together in Earth's night sky would reveal themselves to be separated by vast distances. Conversely, stars that seem far apart from our perspective might actually be neighbors in three-dimensional space. This is one of the most mind-bending aspects of astronomy. When we look up at the night sky, we're seeing a two-dimensional projection of a three-dimensional reality. It's like looking at a photograph of a forest. You can see all the trees, but you can't tell which ones are in front and which are behind without additional information. Modern astronomy has given us that additional information. By measuring stellar parallax, the tiny shift in a star's apparent position as Earth orbits the Sun, we can calculate distances. By analyzing the spectrum of starlight, we can determine whether a star is moving toward us or away from us. These measurements, painstaking and precise, have allowed us to build a three-dimensional map of our cosmic neighborhood. 2 minutes in, 120 light-years traveled, and you'd be passing through regions rich with stellar history. There's the Pleiades, the Seven Sisters, a cluster of hot blue stars born from the same cloud of gas about 100 million years ago. From Earth, we see them as a tight group, but at your speed, you'd see them as they truly are, a loose association of stars, slowly drifting apart as they age. The Hyades cluster would be another landmark, the nearest star cluster to Earth. These stars share a common motion through space, all heading in the same direction like a school of cosmic fish. This common motion was one of the first clues that star clusters were real physical associations, not just chance alignments in the sky. As you race outward, you'd start to encounter the remnants of stellar death. Planetary nebulae, despite their name, they have nothing to do with planets, would appear as glowing shells of gas expelled by dying stars. The Ring Nebula, the Dumbbell Nebula, the Cat's Eye Nebula, each one a star's final exhalation, a last burst of beauty before fading into darkness. These nebulae are fleeting on cosmic timescales, lasting only tens of thousands of years before dispersing into space. But in that brief time, they create some of the most stunning structures in the universe. The Hubble Space Telescope has revealed incredible details in these objects: jets, knots, shells, and filaments of gas glowing in every color of the spectrum. 5 minutes into your journey, 300 light-years traveled, and you'd be entering regions where massive stars live and die. The Cygnus OB2 Association would be nearby, home to some of the most massive and luminous stars in our galaxy. These stellar giants live fast and die young, burning through their nuclear fuel in just a few million years. When these massive stars die, they don't go quietly. They explode as supernovae, briefly outshining entire galaxies. The remnants of these explosions would be scattered throughout your path. The Crab Nebula, created by a supernova observed by Chinese astronomers in the year 1054. The Veil Nebula, the expanding shell from a star that exploded 10,000 years ago. These supernova remnants are more than just cosmic graveyards. They're element factories, creating and dispersing the heavy elements that make planets and life possible. The calcium in your bones, the iron in your blood, the gold in your jewelry, all were forged in the nuclear furnaces of dying stars and scattered into space by supernova explosions. 10 minutes in, 600 light-years traveled, and the scale of the galaxy would start to become apparent. You'd see that stars aren't distributed randomly but follow patterns. Spiral arms would become visible as density waves propagating through the galactic disk. Star-forming regions would appear as bright knots along these arms, while older regions would glow with the redder light of aging stars. The interstellar medium, the gas and dust between stars, would reveal its complex structure. Dark clouds blocking background starlight. Emission nebulae glowing red with hydrogen alpha light. Reflection nebulae shining blue with scattered starlight. Superbubbles carved out by stellar winds and supernovae. This isn't empty space you're traveling through. It's a dynamic, evolving ecosystem where stars are born, live, and die, recycling material in an endless cosmic dance. Modern telescopes operating across the electromagnetic spectrum have revealed this hidden universe. Radio telescopes trace cold molecular gas. Infrared telescopes peer through dust clouds. X-ray telescopes reveal hot gas and violent events 15 minutes into your impossible journey, and you've traveled 900 light-years from Earth. At this distance, you'd be moving through regions that showcase the violent beauty of stellar evolution. The Rosette Nebula would flash by, a cosmic flower spanning 50 light-years, where young stars have blown a cavity in their birth cloud, creating one of the most photographed deep-sky objects. But here's something that would become increasingly apparent. The galaxy isn't static. Everything is in motion. Stars orbit the galactic center, gas clouds collide and merge, spiral arms sweep through space like cosmic tsunamis. What looks peaceful from Earth is actually a maelstrom of activity when you consider the timescales involved. The Sun, for instance, completes an orbit around the galaxy every 230 million years, a galactic year. The last time our solar system was in this position, dinosaurs were just beginning to emerge on Earth. This orbital motion isn't a simple circle. Stars bob up and down through the galactic plane, weave in and out of spiral arms, and occasionally have close encounters with other stars. At your impossible speed, you'd see evidence of these stellar interactions everywhere. Binary stars locked in gravitational embraces, multiple star systems with complex orbital dynamics. Stars that have been flung out of their birthplaces by gravitational encounters now wandering alone through space. 20 minutes in, 1,200 light-years traveled, and you'd encounter one of the most important discoveries in modern astronomy. Exoplanets are everywhere. The TESS mission, launched in 2018, has found thousands of planetary candidates by monitoring the brightness of nearby stars. Many of these worlds are unlike anything in our solar system. Hot Jupiters orbiting closer to their stars than Mercury, super-Earths with no solar system analogue, and planets orbiting binary stars like something out of science fiction. Some of these exoplanets would be particularly intriguing. Kepler 452b, often called Earth's cousin, orbits in its star's habitable zone. Toei 700d, another potentially habitable world discovered by TESS. These planets represent our best chances for finding life beyond Earth, though at your impossible speed, you'd have no time to stop and investigate. The diversity of planetary systems would be staggering. Some stars host multiple planets in resonant chains where orbital periods form simple mathematical ratios. Others have planets on wildly eccentric orbits, swooping close to their stars before racing back out to frigid distances. Some systems are packed with planets orbiting closer than Mercury, while others have planets separated by vast, empty gulfs. 30 minutes into your journey, 1,800 light-years from home, and you'd be passing through regions that tell the story of galactic evolution. Open clusters, groups of young stars born together, would appear throughout the spiral arms. These clusters gradually disperse over hundreds of millions of years, their stars spreading out to join the general galactic population. Globular clusters would start to appear above and below the galactic plane. These ancient stellar cities contain hundreds of thousands of stars packed into spheres just a few dozen light-years across. They're some of the oldest objects in the galaxy, formed over 12 billion years ago when the universe was young. The stars in these clusters have witnessed almost the entire history of cosmic evolution. The chemistry of the galaxy would reveal itself through stellar spectra. First-generation stars formed from primordial hydrogen and helium are almost impossible to find. They lived fast and died long ago. Second-generation stars enriched with heavier elements from the first supernovae are rare but still exist in the galactic halo. Most stars you'd encounter are third generation or later, containing the full, periodic table of elements built up over billions of years of stellar nucleosynthesis. 45 minutes in, 2,700 light-years traveled, and you'd start to see large-scale galactic structures. Giant molecular clouds thousands of times more massive than our Sun would loom like cosmic mountains. These are the birthplaces of star clusters, where gravity slowly gathers gas and dust until nuclear fusion ignites. The Carina Nebula would be a spectacular sight if you could slow down enough to appreciate it. Home to some of the most massive stars known, including Eta Carinae, a luminous blue variable star that could explode as a supernova at any time. When it does, it will briefly outshine the entire galaxy, visible from Earth even in daylight. But massive stars aren't the only story. As you travel, you'd pass through regions dominated by different stellar populations. The thin disk where active star formation continues today, the thick disk containing older stars with different chemical compositions, the stellar halo where ancient stars follow eccentric orbits, some plunging through the disk at high speeds. 1 hour into your journey, 3,600 light-years from Earth, and patterns would emerge from the chaos. Stellar streams, the remnants of small galaxies torn apart by the Milky Way's gravity. Moving groups of stars sharing common origins. Stellar associations spread across hundreds of light-years, all born from the same giant molecular cloud. The local arm, also called the Orion arm, would reveal its true nature. We live in a minor spiral arm, a spur between the major Perseus and Sagittarius arms. From our position within it, it's hard to trace its full extent, but at your impossible speed, you'd see it as a river of stars, gas, and dust winding through space for thousands of light-years. Dark nebulae would create dramatic silhouettes against the starry background. The Horsehead Nebula, the Pipe Nebula, the Dark Doodad, these clouds of dust and gas block the light from stars behind them, creating some of the most recognizable shapes in astronomy. But they're more than just pretty pictures. These dark clouds are where the next generation of stars will form, continuing the cycle of stellar birth and death. As you approach the 1-hour mark, something profound would become clear. You're not just traveling through space, you're traveling through time. The light from each star left at a different moment in the past. That star, 10 light-years away, you're seeing it as it was 10 years ago. That nebula 1,000 light-years distant, its light has been traveling since the Middle Ages. This cosmic light lag means that as you travel outward, you're also traveling backward through history. The farther you go, the younger the universe appears. It's a natural time machine built into the fabric of space-time itself. 90 minutes into your impossible voyage, and you've covered 5,400 light-years. At this distance from Earth, you'd be approaching the far edge of the local arm and beginning to cross the gap toward the Perseus arm. This inter-arm region isn't empty, it's filled with older stars and scattered star-forming regions, but the density is noticeably lower than within the spiral arms themselves. The Perseus arm would loom ahead like a glowing river in space. This is one of the Milky Way's major spiral arms, packed with young, hot stars, nebulae, and active star formation. From Earth, we see parts of this arm in the constellation Perseus, but that's just a tiny slice of a structure that wraps around a significant portion of the galaxy. As you enter the Perseus arm, the difference would be immediately apparent. Star density increases, massive OB associations, groups of the hottest, most massive stars, would blaze with blue-white light. These stellar giants pump out so much energy that they create bubbles in the interstellar medium, carving out cavities filled with hot, X-ray emitting gas. 2 hours in, 7,200 light-years traveled, and you'd encounter some of the galaxy's most extreme objects. The Cygnus X region, one of the most active star-forming complexes in the Milky Way, would showcase stellar birth on an industrial scale. Thousands of young stars, still wrapped in their birth cocoons, would be visible in infrared light. Here's where modern astronomy really shines. The Spitzer Space Telescope, before its retirement in 2020, used infrared vision to peer through cosmic dust and reveal hidden stellar nurseries. The James Webb Space Telescope continues this work with unprecedented resolution, showing us protostars in their earliest stages of formation, surrounded by disks that will eventually form planets. You'd pass by Wolf-Rayet stars, massive stars in their death throes, shedding their outer layers in powerful stellar winds. These stars are so hot they glow primarily in ultraviolet light, and their winds can reach speeds of thousands of kilometers per second. When they finally explode as supernovae, they're among the most energetic events in the universe. The variety of stellar endpoints would be on full display. White dwarfs, the cooling embers of sun-like stars, would be scattered throughout your path. These Earth-sized remnants are incredibly dense. A teaspoon of white dwarf material would weigh as much as a car. Some would be solitary, slowly fading into cosmic obscurity. Others would be in binary systems, stealing material from companion stars and occasionally erupting as novae. Neutron stars would be even more extreme. These city-sized remnants of massive stars pack more mass than our Sun into a sphere just 20 kilometers across. Their density is so great that atoms themselves are crushed, leaving only a soup of neutrons. Some spin hundreds of times per second, sweeping lighthouse beams of radiation across space as pulsars. 3 hours into your journey, 10,800 light-years from Earth, and you'd be deep within the Perseus arm. The galactic ecology would be in full display, a cycle of birth, death, and rebirth playing out on cosmic scales. Supernova remnants from stars that died millions of years ago would be triggering new waves of star formation as their shock waves compress nearby gas clouds. The chemical enrichment of the galaxy would be evident in the spectral signatures of different stars. Each generation of stars adds more heavy elements to the cosmic mix. You'd see this gradient clearly. Stars closer to the galactic center tend to be more metal-rich, while those in the outer regions are more metal-poor. This cosmic metallicity gradient tells the story of how galaxies build up elements over time. 4 hours in, 14,400 light-years traveled, and you'd start to see the true scale of galactic structures. Giant star-forming complexes would stretch for hundreds of light-years. The W3 complex, the W4 complex, the heart and soul nebulae These aren't isolated objects, but parts of a vast network of star formation extending along the spiral arm. The role of dark matter would become increasingly apparent. Although invisible, dark matter makes up about 85% of all matter in the galaxy. Its gravitational influence shapes the orbits of stars, holds the spiral arms together, and extends far beyond the visible disk in a massive halo. Without dark matter, the galaxy would fly apart. The visible matter alone doesn't have enough gravity to hold everything together. You'd pass through regions where the Gaia spacecraft has revolutionized our understanding of stellar motions. Launched in 2013, Gaia has measured the positions and velocities of over 1 billion stars with unprecedented precision. This data has revealed stellar streams, moving groups, and the complex dynamics of the galactic disk in extraordinary detail. 5 hours into your journey, 18,000 light-years from home, and you'd be approaching the far side of the Perseus arm. The view back toward Earth would be spectacular if you could somehow stop and look. Our sun would be lost among billions of other stars, invisible at this distance. The local arm would appear as a minor feature, a small spur between major spiral arms. This perspective shift is humbling. From Earth, we naturally think of ourselves as central, but from out here, our home is just one of countless stars in a minor arm of an ordinary spiral galaxy. Yet this ordinary galaxy is home to extraordinary complexity, planetary systems, organic chemistry, and at least one world where matter has become conscious and started to explore its cosmic surroundings. The interstellar medium would reveal more of its secrets. Magnetic fields invisible to our eyes but detectable through radio observations thread through space, guiding the flow of charged particles and influencing star formation. Cosmic rays, high-energy particles accelerated by supernovae and other violent events, would be zipping past at near-light speed, carrying information about the galaxy's most energetic phenomena. 6 hours in, 21,600 light-years traveled, and you'd be crossing another inter-arm gap, heading toward the outer arm. This region of the galaxy is less well studied than areas closer to Earth, but recent surveys have revealed it to be surprisingly active. Star formation continues even in these outer reaches, fed by gas flowing in from intergalactic space. 7 hours into this impossible journey, 25,200 light-years from Earth, and you'd notice something changing. The galaxy is thinning out. Stars are becoming less densely packed, the bright nebulae less frequent. You're entering the outer arm, sometimes called the Cygnus arm, one of the Milky Way's more distant spiral features. Out here, the galaxy tells a different story. These regions formed later in galactic history, built from gas that took longer to settle into the disk. The stars here tend to be younger and more metal-poor than their inner galaxy cousins. It's like looking at a newer chapter in the galaxy's ongoing book of stellar evolution. But don't mistake outer for empty. The outer arm hosts its own spectacular sights. Massive, star-forming regions still light up the darkness. The NGC 7000 Nebula, the Pelican Nebula, regions where new suns are being born even now, billions of years after the galaxy first formed. The process of star formation never truly stops. It just moves, flows, and evolves with the galaxy itself. 8 hours in, 28,800 light-years traveled, and you'd start encountering some of the galaxy's most exotic objects. Black holes, not the supermassive monster at the galactic center, but stellar mass black holes, the remnants of the most massive stars. These cosmic vacuum cleaners would be invisible except for their effects on nearby matter. Some black holes announce their presence dramatically. In binary systems where a black hole is feeding on a companion star, the infalling material heats up to millions of degrees, emitting X-rays detectable across vast distances. Cygnus X1, the first black hole ever confirmed, would be relatively nearby on your route, a stellar remnant about 15 times the mass of our Sun, locked in a deadly dance with a blue supergiant star. The LIGO and Virgo gravitational wave detectors have revolutionized our understanding of these objects. Since 2015, they've detected dozens of black hole mergers, events where two black holes spiral together and merge, sending ripples through space-time itself. Some of these merging black holes are more massive than theory predicted, suggesting there's still much we don't understand about how these extreme objects form and evolve. 9 hours in, 32,400 light-years from home, and the architecture of the galaxy would be truly apparent. Looking back toward the center, you'd see the spiral arms in all their glory, density waves creating patterns of star formation that persist for billions of years. The Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, all would be visible as glowing rivers of stars and gas. But you'd also see the galaxy's dark side, vast molecular clouds, some containing millions of solar masses of gas and dust, would create dark lanes between the spiral arms. These aren't empty voids, they're the raw material for future generations of stars, waiting for the right conditions to collapse and ignite. The vertical structure of the galaxy would become apparent too. The thin disk where most star formation occurs is only about 1,000 light-years thick, but there's also the thick disk populated by older stars and the galactic halo extending far above and below the plane. You might encounter high-velocity stars kicked out of the disk by gravitational encounters, now following long, looping orbits through the halo. 10 hours into your journey, 36,000 light-years from Earth, and you'd be entering truly frontier territory. Out here, the influence of the galactic center weakens. Stars orbit more slowly, taking longer to complete their circuits around the galaxy. The spiral arm structure becomes less defined, more scattered. This is where our knowledge becomes less certain. The far side of the galaxy is difficult to study from Earth because we have to look through the dense galactic center. Radio telescopes can penetrate the dust, and surveys like the Bar and Spiral Structure Legacy Survey have mapped the locations of star-forming regions throughout the galaxy. But there's still much we don't know about these distant reaches. 11 hours in, 39,600 light-years traveled, and you'd encounter regions where the galaxy is actively growing. Gas streams, possibly stripped from smaller satellite galaxies or flowing in from intergalactic space, would be visible as faint filaments. This cosmic recycling is how galaxies maintain their star formation over billions of years. The small and large Magellanic clouds, our galaxy's most prominent satellite galaxies, would be visible in the distance. These irregular galaxies are caught in the Milky Way's gravitational web, slowly being torn apart by tidal forces. The Magellanic Stream, a river of gas torn from these galaxies, stretches across much of the southern sky as seen from Earth. 12 hours into your impossible voyage, 43,200 light-years from home, and the galaxy would start to feel lonely. Star density continues to drop. The bright star clusters and nebulae that dominate the inner galaxy become rare. Individual stars are separated by greater distances, isolated islands of light in an expanding sea of darkness. Yet even here there are wonders. Ancient globular clusters orbit through this region, relics from the galaxy's earliest days. Some contain stars over 13 billion years old, formed when the universe itself was less than 1 billion years old. These stellar fossils carry the chemical signatures of the early universe, when only hydrogen, helium, and traces of lithium existed. The galaxy's dark matter halo would extend far beyond the visible stars. This invisible scaffolding is what holds the galaxy together, its gravity preventing the rotating disk from flying apart. Dark matter remains one of astronomy's greatest mysteries. We know it exists from its gravitational effects, but its true nature remains unknown despite decades of searching. 13 hours in, 46,800 light-years traveled, and you'd be approaching the edge of the galactic disk. The defined spiral structure has faded away. Stars become scattered, following increasingly eccentric orbits. Some are members of the galactic halo, ancient stars that have witnessed almost the entire history of the Milky Way. Here you might encounter hypervelocity stars, stellar speedsters, racing outward at velocities high enough to escape the galaxy entirely. These stars were likely ejected from the galactic center, flung outward by close encounters with the supermassive black hole. They're cosmic exiles destined to spend eternity wandering the darkness between galaxies. 14 hours into your incredible journey, 50,400 light-years from Earth, and you've reached the edge of the Milky Way's main disk. But the galaxy doesn't end abruptly. It fades gradually, like a city giving way to suburbs, then countryside, then wilderness. Stars become increasingly rare, separated by vast gulfs of nearly empty space. Out here, you'd encounter some of the galaxy's most ancient residents, halo stars formed over 12 billion years ago when the galaxy was still assembling itself from smaller pieces. These stars have different characteristics than disk stars, their metal poor having formed before multiple generations of supernovae enriched the galaxy's gas. They follow wild, eccentric orbits, plunging through the disk at steep angles before swinging back out into the halo. The view back toward the galactic center would be breathtaking. For the first time, you'd see the Milky Way as observers in other galaxies see it, a magnificent spiral, its arms traced by billions of young blue stars and glowing nebulae. The central bulge would glow with the golden light of older stars, packed so densely they merge into a continuous glow. 15 hours in, 54,000 light-years traveled, and you'd be entering the realm of satellite galaxies. The Milky Way doesn't exist in isolation. It's surrounded by a swarm of smaller galaxies, caught in its gravitational web. Some, like the Sagittarius dwarf elliptical galaxy, are being actively torn apart, their stars streaming out in long tidal tails that wrap around our galaxy. These galactic interactions aren't gentle. When galaxies collide, their stars rarely hit each other. Space is too vast for that. But the gravitational forces reshape both galaxies, triggering bursts of star formation and redistributing matter on enormous scales. We see evidence of past mergers in the Milky Way's structure, streams of stars following similar orbits, the remnants of long-dead galaxies. 16 hours into your voyage, 57,600 light-years from home, and the isolation would become profound. Individual stars are separated by light-years. The familiar glow of the galactic disk has faded to a distant shimmer. You're in the galactic halo proper now, a roughly spherical region extending hundreds of thousands of light-years from the galactic center. The halo isn't empty, though. Dark matter dominates here, its invisible mass dwarfing the scattered visible stars. Globular clusters orbit through this space like ancient cities, self-contained stellar systems that have remained largely unchanged for billions of years. Messier 13, the great globular cluster in Hercules, contains hundreds of thousands of stars packed into a ball just 150 light-years across. 17 hours in, 61,200 light-years traveled, and you'd encounter evidence of the Milky Way's violent past. Stellar streams, the shredded remains of smaller galaxies, arc through the halo. The Orphan Stream, the Helmi Stream, the Virgo Stellar Stream, each one tells a story of a galaxy that ventured too close and paid the ultimate price. These streams are fossils of galactic evolution. By studying their stars, astronomers can reconstruct the properties of the original galaxies and understand how the Milky Way grew through cosmic cannibalism. It's a process that continues today. The Sagittarius dwarf is currently being digested, and the Magellanic clouds will eventually suffer the same fate. 18 hours into your journey, 64,800 light-years from Earth, and the Milky Way would appear as a distant island of light. You're now farther from the galactic center than most of the galaxy's globular clusters. The stars here are true wanderers, following orbits that take them hundreds of thousands of light-years from the disk. Some of these distant stars have fascinating origins. They might be former members of dwarf galaxies stripped away during ancient collisions. Others could be hypervelocity stars, ejected from the galactic center and still racing outward. Each star has its own story, its own journey through cosmic time. 20 hours in, 72,000 light-years traveled, and you'd be approaching the Magellanic clouds. These irregular galaxies are the Milky Way's most prominent companions, visible from Earth's southern hemisphere as fuzzy patches in the night sky. The large Magellanic Cloud contains about 10 billion stars, while the small Magellanic Cloud has several billion. Up close, these galaxies would reveal their chaotic beauty. Unlike the ordered spirals of the Milky Way, the Magellanic Clouds are irregular, their structures disrupted by gravitational interactions. The Tarantula Nebula in the large Magellanic Cloud would be spectacular, a star-forming region so vast and bright it would be visible to the naked eye from Earth if it were placed at the distance of the Orion Nebula. The Magellanic Stream would be visible as a faint river of gas torn from the clouds by tidal forces and stretching across the sky. This gas will eventually fall into the Milky Way, providing fuel for future star formation. It's a reminder that galaxies aren't isolated. They interact, exchange matter, and evolve together. 24 hours into your impossible journey, 86,400 light-years from Earth, and you'd be truly between galaxies. The Milky Way would appear as a magnificent spiral, but no longer dominating the sky. Other galaxies would become visible in the distance. Andromeda, still over 2 million light-years away, would appear as a faint smudge, slowly growing larger. The space between galaxies isn't completely empty. The intergalactic medium contains extremely diffuse gas, mostly hydrogen, heated to millions of degrees. This gas is so thin that a volume the size of Earth might contain only a few atoms. Yet there's so much space between galaxies that the intergalactic medium contains more ordinary matter than all the galaxies combined. As you travel through this cosmic void, relativistic effects would become even more extreme. At your impossible speed of 1 light-year per second, the cosmic microwave background radiation, the afterglow of the Big Bang, would be blue-shifted into deadly gamma rays in your direction of travel. Behind you, it would be redshifted into long radio waves. 28 hours into your journey at 1 light-year per second, 100,800 light-years from Earth, and the Milky Way would finally appear as a complete spiral galaxy behind you, no longer filling your entire view. You're now in true intergalactic space, the vast emptiness between the islands of stars that populate our universe. But empty is a relative term. Even here, there are surprises. Rogue stars, ejected from their home galaxies by gravitational encounters, wander through the darkness. Some astronomers estimate there could be as many stars between galaxies as within them, a lonely population of cosmic nomads, invisible to our telescopes but revealed by careful theoretical calculations. Dwarf galaxies would start appearing in greater numbers. The local group, our galactic neighborhood, contains over 80 known galaxies, most of them small dwarfs containing just millions of stars rather than billions. There's Fornax, Sculptor, Draco, Leo the Fine, and 2. a whole menagerie of minor galaxies orbiting the Milky Way like moths around a flame. These dwarf galaxies are laboratories for understanding dark matter. They're so small and faint that dark matter makes up over 99% of their total mass. Without dark matter's gravitational glue, these galaxies would have dispersed long ago. The fact that they exist at all is one of our strongest pieces of evidence for dark matter's reality. 36 hours in, 129,600 light-years traveled, and patterns would emerge from what seemed like random distribution. Galaxies aren't scattered uniformly through space. They're organized into groups, clusters, and enormous filaments that stretch across the cosmos. You're traveling along one of these cosmic highways, following the gravitational roads that connect galaxies across millions of light-years. The local group would reveal its true structure. It's dominated by two giant spirals, the Milky Way and Andromeda, with a third large galaxy, Triangulum, playing a supporting role. These three galaxies and their satellites are bound together by gravity, destined to merge over the coming billions of years into a single, massive, elliptical galaxy. Computer simulations show this future merger in detail. In about 4 billion years, Andromeda and the Milky Way will make their first close pass. The galaxies will distort each other, throwing out long tidal tails of stars. They'll separate, then fall back together, eventually merging into a single galaxy sometimes called Milkomeda or Milkdromeda. Our night sky will be spectacular during this merger, filled with star formation and cosmic fireworks. 2 days into your journey, 172,800 light-years from home, and smaller members of the local group would pass by like cosmic islands. Many of these galaxies are barely visible from Earth, requiring long exposures with large telescopes to detect. But each one is a complete stellar system, with its own history of star formation, its own planetary systems, possibly its own forms of life. The diversity would be striking. Elliptical galaxies, their star formation long since ended, glowing with the red light of aging stars. Irregular galaxies, chaotic and beautiful, still forming new stars in scattered bursts. Dwarf spheroidals, so diffuse they're barely distinguishable from the background, yet held together by massive dark matter halos. 3 days in, 259,200 light-years traveled, and you'd be approaching the halfway point to Andromeda. The space between the Milky Way and Andromeda isn't empty. Streams of gas connect the galaxies, and a population of small galaxies occupies the space between. Some of these galaxies are likely being stretched and distorted by the gravitational pull of the two giants. High-velocity clouds of gas would be visible, racing through intergalactic space. Some of these clouds are remnants of disrupted galaxies. Others might be pristine material, unchanged since the early universe, falling into the local group for the first time. When these clouds hit a galaxy's disk, they can trigger bursts of star formation, seeding new stellar generations. 4 days into your impossible voyage, 345,600 light-years from Earth, and Andromeda would begin to dominate the view ahead. Our nearest large galactic neighbor is a spectacular sight, a spiral galaxy somewhat larger than the Milky Way, containing perhaps 1 trillion stars. From Earth, we see it nearly edge-on, but from your vantage point, its spiral structure would be clearly visible. Andromeda has its own collection of satellite galaxies. M32 and M110 are the most prominent, but there are dozens of smaller dwarfs orbiting the giant spiral. These satellites show signs of past interactions. M32 appears to be the stripped core of a once larger galaxy, its outer regions torn away by Andromeda's gravity. 5 days in, 432,000 light-years traveled, and you'd see evidence of past collisions in Andromeda's structure. Streams of stars loop around the galaxy, the remnants of cannibalized satellites. The galaxy's disk shows warps and distortions, evidence of gravitational interactions. Star clusters of different ages trace out past episodes of star formation triggered by these cosmic encounters. Recent observations have revealed that Andromeda's history is more violent than the Milky Way's. It appears to have undergone a major merger about 2 billion years ago, consuming a galaxy perhaps a quarter of its current size. This merger likely triggered the burst of star formation that created many of Andromeda's globular clusters. 1 week into your journey, 4,800 light-years from home, and you'd be entering Andromeda's outer halo. Like the Milky Way, Andromeda is surrounded by an extended sphere of dark matter, ancient stars, and globular clusters. The transition from intergalactic space to galactic halo is gradual, marked by slowly increasing stellar density. Andromeda's globular clusters would be magnificent. The galaxy hosts over 400 of these ancient star clusters, compared to about 150 for the Milky Way. Some are incredibly luminous, visible from Earth with small telescopes despite the enormous distance. Each cluster is a fossil from the galaxy's formation, preserving conditions from over 12 billion years ago. 8 days into your impossible journey, 691,200 light-years from Earth, and you'd be plunging through Andromeda's spiral arms. The view would be spectacular beyond words. Massive star-forming regions, each containing enough gas to form millions of suns, would blaze with the blue light of young stars. Dust lanes would create dramatic silhouettes, tracing the density waves that maintain the spiral structure. Andromeda's central black hole, with a mass of about 100 million suns, would anchor the galaxy's core. This is significantly more massive than the Milky Way's central black hole, which weighs in at only 4 million solar masses. The difference tells us something profound about how galaxies evolve. More massive galaxies tend to have more massive central black holes, suggesting a deep connection between galactic and black hole growth. 10 days in, 864,000 light-years traveled, and you'd emerge from the far side of Andromeda, looking back at 2 magnificent spirals, your home galaxy and your first major galactic neighbor. From this vantage point, the future collision between these 2 giants would seem inevitable. They're approaching each other at about 110 kilometers per second, drawn together by their mutual gravitational attraction. But now, ahead of you, the true scale of the universe would begin to reveal itself. Beyond the local group lies a vast expanse before you reach the next major concentration of galaxies. This is one of the universe's great mysteries. Why is matter so unevenly distributed? Why do we have dense clusters separated by enormous voids? 2 weeks into your journey, 1,209,600 light-years from home, and you'd be entering the cosmic wilderness. The galaxies here are more isolated, separated by millions of light-years. Each is an island universe, evolving in relative isolation, following its own path through cosmic time. You'd pass galaxies that challenge our understanding of physics, ultra-diffuse galaxies as large as the Milky Way but containing only 1% as many stars. How do these ghostly giants hold together? Dark matter must dominate them even more than normal galaxies, but we still don't fully understand their formation. 3 weeks in, 1,814,400 light-years traveled, and patterns would emerge on even larger scales. Galaxies aren't just grouped into clusters, the clusters themselves are organized into superclusters, vast associations spanning hundreds of millions of light-years. You're approaching the edge of our local supercluster, centered on the Virgo cluster. The Virgo cluster would loom ahead like a cosmic metropolis. Over 1,300 galaxies packed into a region just a few million light-years across. At its heart sits M87, a giant elliptical galaxy containing several trillion stars. This was where the Event Horizon Telescope captured the first image of a black hole's shadow, a supermassive monster weighing 6.5 billion solar masses. 1 month into your voyage, 2,592,000 light-years from Earth, and you'd be witnessing galactic evolution in action. In dense cluster environments, galaxies interact constantly. You'd see ongoing mergers, galaxies distorted by tidal forces, and streams of gas stripped away by the cluster's hot intergalactic medium. Galaxy harassment would be visible everywhere. When a smaller galaxy passes too close to a larger one, gravitational forces can strip away its gas, shutting down star formation. The cluster environment transforms spiral galaxies into ellipticals, blue galaxies into red, active galaxies into passive ones. It's evolution by interaction, natural selection on a cosmic scale. 6 weeks in, 3,628,800 light-years traveled, and you'd be crossing the Virgo cluster. The density of galaxies here is hundreds of times greater than in the local group. Giant ellipticals, each containing trillions of stars, would pass by like cosmic whales. Smaller spirals, their arms distorted by gravitational interactions, would show the stress of living in such a crowded neighborhood. The intracluster medium would reveal itself through its effects. This superheated gas, reaching temperatures of millions of degrees, fills the space between galaxies in the cluster. It's so hot it emits X-rays, creating a diffuse glow visible to space telescopes like Chandra and XMM Newton. This gas contains more ordinary matter than all the galaxies in the cluster combined. 2 months into your impossible journey, 5,184,000 light-years from home, and you'd emerge from the far side of the Virgo cluster. Behind you, over 1,000 galaxies would glow in a concentrated region. Ahead, another vast expanse of relatively empty space, the cosmic voids that make up most of the universe's volume. These voids aren't completely empty. They contain scattered galaxies, but at much lower density than clusters. Void galaxies evolve differently than their cluster cousins. With fewer neighbors to interact with, they can maintain their gas supplies and continue forming stars for longer periods. They're cosmic hermits, following their own evolutionary paths. 3 months in, 7,776,000 light-years traveled, and the large-scale structure of the universe would be undeniable. You're traveling along cosmic filaments, the web-like structure that connects clusters across billions of light-years. These filaments are rivers of dark matter and gas, channeling material toward the dense nodes where clusters form. The discovery of this cosmic web is one of modern astronomy's greatest achievements. It began with redshift surveys in the 1980s, mapping the three-dimensional positions of galaxies. What emerged wasn't random distribution, but organized structure, walls, filaments, and voids arranged in a pattern that spans the observable universe. 4 months into your voyage, 10,368,000 light-years from Earth, and you'd encounter galaxy groups of every size and configuration, compact groups where galaxies are so close they're practically touching. Loose associations spread across millions of light-years, fossil groups where all the major galaxies have already merged, leaving a single giant surrounded by dwarfs. Each group tells a story. The Stephan's Quintet, which you might pass, shows 5 galaxies locked in a complex gravitational dance. 4 are genuinely interacting, their mutual gravity creating tidal tails and triggering starbursts. The 5th is actually a foreground galaxy only appearing associated by line of sight, a reminder that appearance can be deceiving in astronomy. 6 months into your impossible journey, 15,552,000 light-years from Earth, and you'd be witnessing the universe at scales that dwarf human comprehension. The local supercluster, which contains our local group, and the Virgo cluster, would be shrinking behind you. Ahead, other superclusters would appear like cosmic continents, separated by vast oceanic voids. The Perseus-Pisces supercluster would stretch across your path, a chain of galaxy clusters extending over 300 million light-years. This is one of the dominant structures in our region of the universe, containing thousands of galaxies organized into a filamentary structure. The Perseus cluster, one of the brightest X-ray sources in the sky, would be a prominent landmark. At the heart of the Perseus cluster sits NGC 1375, a giant elliptical galaxy with a supermassive black hole that's been caught singing. The Chandra X-ray Observatory detected pressure waves emanating from the black hole, sound waves with a frequency 1,000,000 billion times lower than human hearing. It's the deepest note in the universe, a B-flat 57 octaves below middle C. 8 months in, 20,736,000 light-years traveled, and you'd encounter phenomena that push the limits of physics. Blazars, supermassive black holes shooting jets of material almost directly at Earth, would appear as brilliant beacons. These jets, traveling at 99% the speed of light, can outshine entire galaxies and be visible from billions of light-years away. Speak. The variety of active galactic nuclei would be staggering. Seyfert galaxies with their bright variable cores, radio galaxies launching jets that extend for millions of light-years, quasars, the most luminous objects in the universe, powered by black holes consuming matter at prodigious rates. Each type represents a different viewing angle or evolutionary stage of galactic centers. 1 year into your voyage, 31,536,000 light-years from home, and you'd be approaching cosmological distances where the universe's expansion becomes noticeable. Galaxies aren't just moving through space. Space itself is expanding, carrying galaxies along like raisins in rising dough. The farther away a galaxy is, the faster it appears to be receding. This cosmic expansion was one of the most shocking discoveries of the 20th century. Edwin Hubble found that galaxies are moving away from us, with more distant galaxies receding faster. This relationship, now called Hubble's law, led to the realization that the universe is expanding and, by running the clock backward, that everything began in a Big Bang 13.8 billion years ago. 18 months in, 47,304,000 light-years traveled, and you'd be crossing the Coma supercluster, one of the nearest massive superclusters. The Coma cluster at its heart contains over 1,000 galaxies in a sphere just a few million light-years across. It's so massive that its gravity bends light from more distant galaxies, creating distorted arcs and multiple images, gravitational lensing in action. Fritz Zwicky studied the Coma cluster in the 1930s and made a shocking discovery. The galaxies were moving too fast to be held together by the gravity of visible matter alone. He proposed the existence of dark matter, invisible material providing the extra gravity. It took decades for his idea to be accepted, but now we know dark matter dominates the mass of all galaxy clusters. 2 years into your impossible journey, 63,072,000 light-years from Earth, and the universe would reveal its hierarchical structure. Superclusters themselves are organized into even larger patterns. The Great Wall, discovered in 1989, is a sheet of galaxies extending over 500 million light-years. The Sloan Great Wall, found in 2003, is even larger. These walls and filaments surround enormous voids, regions where galaxies are rare. The Botes void, which you might skirt, is a roughly spherical region 330 million light-years in diameter containing only a handful of galaxies. It's sometimes called the Great Nothing, a cosmic bubble in the universe's foam-like structure. 3 years in, 94,608,000 light-years traveled, and you'd encounter the universe's construction sites, protoclusters, regions where galaxy clusters are still forming, would show the universe's structure caught in the act of assembly. These regions are rich in star-forming galaxies, their activity triggered by the increasing density as gravity draws material together. The Spiderweb Galaxy protocluster would be a spectacular example. Discovered by the Hubble Space Telescope, it shows dozens of galaxies falling together, connected by filaments of gas like a cosmic spider's web. In a few billion years, these galaxies will merge into a massive cluster, but for now they're caught in the act of assembly. 4 years into your voyage, 126,144,000 light-years from home, and you'd be entering regions where our detailed knowledge begins to fade. The observable universe extends about 46 billion light-years in every direction, but our surveys have only mapped a fraction of it in detail. Each new deep survey reveals thousands of previously unknown galaxies. The James Webb Space Telescope is revolutionizing our view of these distant regions. Its infrared vision can peer through cosmic dust and see galaxies whose light has been stretched by the universe's expansion. It's finding galaxies that formed when the universe was just a few 100 million years old, challenging our theories about how quickly structure can form. 5 years in, 157,680,000 light-years traveled, and you'd witness cosmic evolution in action. Looking outward in space means looking backward in time. The galaxies here emitted their light 500 million years ago. They appear younger, smaller, more irregular than nearby galaxies. Star formation rates were higher in the past, feeding on the denser gas available in the younger universe. The universe's chemical evolution would be apparent. Early galaxies contain mostly hydrogen and helium, the elements formed in the Big Bang. Heavier elements, what astronomers call metals, are less abundant. You're seeing the universe before multiple generations of stars had time to create and disperse the elements that make planets and life possible. 6 years into your impossible journey, 189,216,000 light-years from Earth, and gravitational lensing would become a common sight. Massive galaxy clusters bend space-time, creating cosmic telescopes that magnify more distant objects. You'd see galaxies distorted into arcs and rings, their light bent around intervening masses. If you enjoyed this video, I am sure you will love this other one at the left side of the screen. Why light speed? Travel would destroy us before we even arrive. In this video, discover the terrifying physics that make light speed travel not just impossible, but deadly. See you there.